Hi, everyone. Today, myself and my colleague Jeff are going to present from ARM about the LBBR requirements for LinuxBoot firmware. So I'll start by saying that the initiative is part of our ARM System Ready program. So let's talk a little bit about ARM System Ready first. So ARM System Ready is a compliance certification program that aims at providing consistency of running software on the ARM devices spanning from server to the edge and IoT. Our vision is that for software to just work seamlessly on this diverse ecosystem of hardware. And to do this, we are focusing on standards and requirements for key components in the software stack that are common across the ecosystem, like booting, the operating system, and hypervisor and middleware components. The program is divided into 4 bands that were driven by the needs of the different operating systems and the market segments. The bands are the LS, IR, ES, and SR. For this specific presentation, we'll be talking a lot about the LS band. That's the band that is focusing on standards for ARM servers that target the LinuxBoot based firmware. On the other side, on the right-hand side, you will find the SR band, which is standards for ARM servers and workstations using generic off-the-shelf operating systems. And then the IR and ES bands target more around the embedded ecosystem with different operating system targets. This program is built upon a foundation of hardware and firmware requirement specifications. The hardware requirements are essentially in the BSA and the base system architecture specification, which is a common requirements document across all devices. Version 1.0 was published in October of last year, and it includes things that are necessary in the silicon and in the platform hardware to offer standard interfaces or standard hardware components for the OS to boot and run. So it focuses on the view from the operating system and hypervisor. We also have market segment specific extensions or additional documents that go along with the BSA. The first one is the SBSA, or the server BSA, with version 7.0 published earlier this year. Now, on the firmware side, we have one document, main specification called the BBR, or the base boot requirements, which defines a number of recipes that allow variations on the firmware requirements according to the market segment. We call those recipes, and the 3 main recipes we have are the SBBR, EBBR, and LBBR. So let's talk about these firmware recipes. The SBBR is the recipe that enables system-ready SR and ES. It offers the most complete OS support with standard and complete requirements around UEFI, ACPI, SMBIOS, and the trusted firmware and secure interfaces, or interfaces to the secure world firmware. We have then the EBBR, on the other hand, which is tailored for the system-ready IR band, and it includes reduced UEFI requirements and device tree. And then the LBBR in the middle, which is the focus of this presentation, is targeting the system-ready LS, and it is focusing on requirements for booting using the LinuxBoot based firmware on ARM servers. We are working on version 1 of the LBBR definition to be published targeting the April of next year in an update to the BBR document. Now, if you put the LS and SR bands hand in hand, you will notice some commonalities and some differences as well. Both are targeting ARM servers. Both require the same hardware requirements in the silicon and the platform hardware using the SBSA and the BSA requirements. The main difference is the firmware recipe. So if you use the LBBR firmware recipe on that SBSA compliant server hardware, it opens up generic off-the-shelf operating systems, including the wide range of Linux distros, BSDs, Windows, and VMware that run on ARM 64 machines. With LBBR, at least initially with LBBR v1, we target the hyperscalers and CSPs integrated, vertically integrated environments with Linux distros that can boot from LinuxBoot. So we're talking a lot about LinuxBoot and system-ready LS. So as you know, LinuxBoot is an alternative firmware stack. The kernel and the uroot acts as a substitute or a big part of the normal world firmware component on these ARM servers. The system-ready LS is designed specifically to use this LinuxBoot recipe. We haven't certified any platforms with the system-ready LS yet. We are targeting certifications in April that go along with the publication of the firmware requirements and availability on commercial systems. So let's talk a bit about LBBR then. We said that this is the recipe for firmware requirements or for base boot requirements that's part of system-ready LS. It's included in the BBR document itself. The LBBR v1 or the first version of the LBBR recipe is we are taking a phased approach in defining these recipes. So the first version is a practical set of requirements that match the existing implementations available today on ARM servers that use LinuxBoot, while standardizing what is presented to the final operating system in order to have this interoperability of allowing different OS distros of running on these machines. Our goal is to continue to evolve the LBBR recipes to reduce the dependency on the underlying UEFI-based firmware implementations and improve the standard firmware interfaces that are exposed to the final OS. So with this diagram, you can see an overview of the LBBR v1. This is built using some minimal UEFI-based firmware. This could be something derived from Tiano core like EDK2, but we are not requiring that. It could be any other firmware that substitute that can provide the same interfaces. And that firmware runs before the LinuxBoot kernel and uroot is loaded. The idea is that that minimal firmware that runs before LinuxBoot produces the runtime footprint that is needed to be consumed by the final operating system. And that includes, since these are servers, you have ACPI and SMBIOS requirements that the OS expects. But we also have minimal UEFI runtime services that need to be present, at least the framework for the UEFI runtime services in order to be published to the final OS. In this recipe, all these components are built by the UEFI firmware itself before LinuxBoot is loaded. LinuxBoot itself uses those interfaces like as ACPI and the UEFI if needed, and then preserves them in memory to be used by the final operating system. And the transition happens using kexec. So between LinuxBoot and the final Linux OS, there is a kexec. So this limits the targets of the final operating system to be Linux-based distros. Now, since we are saying ACPI and SMBIOS are required on this LBBR v1 recipe, if you look at the Linux kernel documentation, the only valid legal way for the Linux kernel or for any OS to find the ACPI tables on ARM64 machines is using the UEFI system table pointer from the UEFI configuration table. So you have in the UEFI system table, you have these configuration table pointers, and one of them points to the SM BIOS and the other one points to the ACPI in memory. Because of that, in this minimal version of LBBR, you need this framework to be implemented, at least the runtime portion of the UEFI system table. So you can skip, for example, the boot services. Those are not consumed by LinuxBoot itself or by the final OS, because they only exist before LinuxBoot is loaded, or before, actually, I should say before exit boot services is called. But the runtime footprint that includes the configuration tables for the SM BIOS table, ACPI, as well as the UEFI runtime service pointers need to exist. And they can't be null pointers, because once Linux sees a UEFI system table in there, it expects that these pointers exist. Now, we're saying that you don't have to fully implement all those services. So some of them it may be legal to return EFI unsupported, but the ABI needs to exist and needs to be valid, and then it can return unsupported. And the details will be published as part of the LBBR recipe in the specification. Now, moving forward in the future, we are looking at taking advantage of UEFI, more complete UEFI services that can be produced by LinuxBoot itself. So that includes, for instance, the work that is being done upstream in the UEFI payload package in EDK2. Project started in the LinuxBoot branch of EDK2, led by Google. You can see here links to the design, to the approach, and the design details and the status of where this project is. There's also a Slack channel under the OSFC Slack server, so you can join the conversation there as well. And with the ability to load UEFI from LinuxBoot, now you have boot services in addition to runtime services, and that opens up the door to be able to boot the OS distros in a standard approach that includes non-Linux distros as well, like Windows and VMware and BSDs. So this approach could be used in future LBBR recipes. It allows us to reduce the dependency on UEFI before LinuxBoot. So you don't have to have the minimal UEFI firmware implementation. You could just carry this payload, the UEFI payload, on top of LinuxBoot. It also allows us to presenting more complete UEFI interfaces to the final OS, like I said, including the boot services. And with this approach, you really get to a point where the SR and the LS bands of system ready start becoming very similar, just using different firmware. So one uses LinuxBoot, the other one could be using more complete UEFI firmware like EDK2. But at the end of the day, what they are presenting to the final OS look very similar in terms of base boot requirements. There is some development work needed here to enable ARM64 with this approach, and that's what we are going to look at next after LBBR v1. So this diagram kind of shows an evolution roadmap of the LBBR recipes on ARM Linux boot-based servers, starting with v1 today, with the minimum UEFI firmware and the LinuxBoot kernel on top, and kexec to the final OS. UEFI interfaces produced by this minimal UEFI firmware. And then moving on, as we put this UEFI ABI or UEFI payload on top of LinuxBoot, then you start shifting the need for producing some of these, maybe majority of these interfaces to be done in the UEFI ABI itself, and you introduce new interfaces like the UEFI boot services. There are still questions on how much is needed to be consumed by LinuxBoot itself, so some ACPI may still be needed before, so you can see that there are still question marks and some investigation that needs to be done here. And like I said, that puts us at a place where SBBR and LBBR start looking very similar from an OS point of view, even though the firmware buildup is very different. And then moving on from specifications and requirements to implementations, ARM would like to highlight the Ampere Ultra Mount Jade server. This is an ARM System Ready SR certified machine. It is also an OCP accepted design machine, the first that's accepted in the Open Compute project from ARM-based servers. It offers both commercial and open source firmware, including EDK2 SBBR compliant, as well as LinuxBoot based firmware. Ampere even offers additional integration options that allow for easier and better transition from the UEFI to LinuxBoot. We also have the Raspberry Pi with its open source firmware project, and that's already certified as ES and IR. We're using the Raspberry Pi as a proof of concept device for its popularity and availability, not because it's a server or going to be System Ready LS certified. That's not the target. But the firmware is open source, the hardware is easily available. It makes it easy in the hands of developers to do the LinuxBoot integration and upstream development. Now I'll hand over to Jeff.
Thanks, Samer. So, and then as well as with the Raspberry Pi being a target SBSA QEMU, which is a QEMU platform that aims to be SBSA and SBBR compliant. Fujitsu has previously done work to get LinuxBoot up and running on this QEMU system using similar approaches to what exists today in LinuxBoot, and that includes building a UEFI image and then using the tools in the LinuxBoot repositories to remove the Dixies and the shell and in place swap in your LinuxBoot image. Next slide. So LinuxBoot on top of EDK2 is sort of the first approach to getting LinuxBoot up and running. There's a mountain of experience and contributions and existing platforms doing this. So at ARM, we're kind of building on top of the work of Ampere and Fujitsu and Google. And we've taken steps to publish 3 guides for 3 proof of concepts. So that being the ARM Neoverse FVP fixed virtual platform, the SBSA QEMU platform, and a Raspberry Pi. All of our reference implementations have open source firmware. So rather than using the tools that LinuxBoot, that people in the LinuxBoot community have been using to pull out the shell and all these Dixies, we can just go straight into the EDK platform or EDK2 platform firmware and just not build them into our final image. Next slide. So the first step to do this is pretty straightforward and standard. You build your uroot init RAM or init RAM FS and your Linux kernel into a single image. And rather than using those tools to swap it in place of the shell, we can just create a new EDK2 package reusing the shell GUID. And as you can see, there's a path to where the image is inside of that package. Next slide. And once we've created this LinuxBoot package, all we have to do is remove the shell package from our platform FDF file. We can then include our LinuxBoot package. And since it's using the same GUID, when we go to enter the shell in UEFI, it will instead execute LinuxBoot. And the last step is to increase the size of our final image. So currently, kernel compression is kind of a tricky thing in ARM, and this is a first proof of concept system. So we've sort of made the firmware volume size pretty large, just so we know we can fit everything. But in the future, we intend to shrink the size down. As you can see in the second lower box, there is a change in the size to about 10 megabytes. Next slide. So As I mentioned before, this is up and running today on 3 systems, the first one being the ARM FEP. The FEP is a complete simulation of an ARM system. It has the processors, memory, peripherals, the whole 9 yards. So this process of booting LinuxBoot on these ARM systems is pretty straightforward, and it's pretty standardized right now across all of these proof of concepts. It first requires turning on the system and doing manual intervention to get into the boot manager, selecting the UEFI shell in the boot manager, which is actually our LinuxBoot image. Once we have selected the UEFI shell, it will boot us into Linux kernel, the first Linux kernel, and uroot. From there, we can mount our final OS drive, set up our kexec, and execute our kexec. In this instance, we've booted into a BusyBox image. Next slide, please. So the FEP is great. It's a fully functional, fully featured system, but it's not very familiar to a lot of developers. QEMU, on the other hand, is very approachable. Many people are quite familiar with it. And for the most part, it has a lot of good features similar to FEP. So it's, as I said earlier, it's, we're targeting to have it SBSA compliant and SBBR compliant, but it has things like GigV3, generic timers, watchdogs, etc. And so it has the emulated features that really count. And thankfully, the process is almost exactly the same. Building the firmware image is the same across the systems, or the changes that you need to make are the same. This time when we're booting it, same manual step, we hit escape to get into UEFI. We go to the boot manager, select the shell. Next slide, please. We enter the Linux kernel and uroot. We're greeted with our command line, and we get to mount our drive and kexec into the final image. This is kind of tedious right now, but this process can be automated using the tools inside of uroot like uinit and system boot. And then on this demo, we actually booted into the ARM ACS architectural compliance suite, test suite, I should say. And it is a BusyBox image that also runs things like firmware test suite, as well as some other interface gathering, so we can see how compliant a system is in terms of where it compares to our SBBR and SBBA specifications. Next slide. Thank you. So finally, we're going to follow the exact same process again, but this time on real hardware. So the Raspberry Pi, as stated before, it's not a server. It's not going to be fully compliant, but surprisingly, the firmware story is pretty familiar. It's pretty similar. It has UEFI, it has ACPI and SMBIOS, and it's quite possibly the most accessible piece of hardware ever. So we build it very similar as the others. There's a couple more quirks, but after the image is built, we could go ahead and get into the UEFI menu, go into the boot manager, select the UEFI shell again, which is our LinuxBoot image. Next slide, please. And this time, when we enter uroot, we set up our kexec, similar as before. We mount our drive, select our image, select our initRD and our root, or append our root, I should say. Once again, this can also be automated with uroot or sorry, with system boot or uinit. Next slide. And after we've executed our kexec, we're greeted with the Fedora 34 operating system. And as a bonus, I catted OS release, and I looked at the ACPI tables and have seen that they are there, they exist. these things have been passed through the K-exec to the final operating system. So those are cool. The proof of concepts, they work. And we have a lot of work for the next iteration of LBBR, as Samer said, with the ABI. But we still have some future work with this first iteration. One of the big things is seamless booting. So as mentioned before, Ampere has upstreamed a LinuxBoot boot manager library that allows the ARM systems to completely bypass any sort of manual intervention to go to the UEFI shell. Instead, you just provide your LinuxBoot image and a GUID to it, and it boots straight to that, so that will bring you straight into uroot, and I'll talk a little bit more about that in a second, as well as working with the uroot tools like System Boot, the System Boot bootloaders, and Unit, so that you can have a one button, or I should say, a one touch experience from turning on the power and getting to your final OS. The next thing that we're focusing on is reducing the size of the firmware image and removing all of those Dixies that are no longer needed. All of these proof of concepts had all of the Dixies that were originally in the image. So that's the next step, as well as looking into how we can compress down our final firmware volume size, whether that be by some kind of kernel compression or init-ramfs compression. And lastly, we want to contribute everything we've done and upstream it to EDK2 to serve as kind of a reference implementation or guidelines so that other people can do the same with their systems. And we're going to continue to update that LinuxBoot resources repo as the work progresses. Next slide, please. So as I said before, seamless transitions or seamless booting is something that's very desirable. It's not feasible to always go into a manual boot screen and select the device and then do your K-exec. We know it works. We have this working on QEMU. We're starting to get it working on the Raspberry Pi. We just don't have it ready in time for this presentation. But as soon as we have the Linux Boot Manager library integrated and we have System Boot up and running as we want it to, those will be in the repo with the resources and in our final upstreams. Next slide. And we've already started work on removing all of the unnecessary Dixies. Starting with the SBSA QEMU platform, we've removed around 30 Dixies, and we're testing it against a normal system that runs UEFI with firmware test suite, FWTS. And thanks to the Linux Boot Manager library, we can completely remove all kinds of UI and console Dixies as well. There's nothing that a user has to see or touch. It can just go straight into the first stage Linux kernel. And once all that is done as well, this will be in our platforms that we upstream, so it can serve as a good starting point for someone else trying to migrate their firmware from full EDK2 down to a slimmed down version of EDK2. So that's what I have. This is links to our references as well as to the repo where our work can be found. Please feel free to reach out, reproduce our work, contribute, or raise issues. Thank you.